So the next talk is on learning heuristic search via imitation. It's work from Sebastian Scherer's group at Carnegie Mellon University, and it's presented by Mohak Bhardwaj.
So good afternoon, everyone. Today I'm going to discuss an efficient approach to training heuristic policies for search-based motion planning. This work has been done in collaboration with Sanjiban and our advisor, Sebastian at AirLab at CMU. So the work at our lab is done on UAVs of all sizes. And one of the major projects that we have is autonomy for this full-scale helicopter, which is the Boeing unmanned Little Bird. So this helicopter has to fly at high speeds of up to 60 meters per second, and it has an onboard laser which helps it see the world at a 1 kilometer radius. And what makes planning for this helicopter hard is real-time requirements and differential constraints which limit the reachability of the system. And as you can see, this helicopter has to essentially fly in many different environments, and we want a robust planning module that has consistent performance across all of these environments. So, and we see that the environment that the robot operates in actually has a lot of effect on these planning algorithms. So on the left, you can see this is an environment with a sparse obstacle like a tower. And in this case, even a smooth trajectory optimization can successfully warp the path around that single obstacle. But on the right, if you have a hilly terrain which is sort of cluttered, sampling-based planner performs better. And what we want is for our approach to find these trade-offs on its own. So what happens when we run like the state-of-the-art optimal planning algorithm? So in this case, it does not use any context from the environment. In order to find the optimal path, it expands a lot of edges that are in collision. It does not know that due to the wires and the no-flying zones, like it should not focus its search at the center, along the center line, but should focus elsewhere. And historically, the focus of motion planning has been on things like on worst-case performance. So initially, it was about computational complexity and completeness. And then with the advent of sampling-based planning, it became stuff like probabilistic completeness, or things like asymptotic optimality, that is finding the optimal path given infinite number of samples. We, on the other hand, would like to bring the spotlight to expected performance of these planners. So what we want is, given a distribution over problems, so say wires or a canopy of trees, we want a planner to automatically adapt itself so that it increases the expected performance. And in this work, we talk about how learning heuristics for graph search can actually achieve this idea of an adaptive motion planner. So this is a brief outline of our talk. And I'll start off with the motivation. So why do we need heuristics in graph search? So graphs are general representations that work across many domains. So while we use it in non-holonomic path planning, they've also been shown to be scalable for 7D robot arm planning, and also like AI game playing like AlphaGo, which uses a variant of MCTS. And in this scenario, a graph generally consists of a set of vertices and edges, where the vertices are states of the robot and edges are dynamically feasible connections between them. And a search algorithm uses this graph and a world representation and a heuristic to evaluate nodes to grow the search tree from start to goal and return a path from a start to goal vertex. But the critical computational bottleneck in heuristic search is edge evaluation. So if you're working with a manipulator, it involves like geometrical operations to check your robot mesh with the world mesh. And in the case of a UAV, it requires checking for collisions against the point cloud. And for real-time performance, we need a heuristic that essentially guides the search to minimize number of collision checks till a path is found. And we think of this in terms of anytime motion planning. So in anytime motion planning, the objective is generally to quickly find a feasible solution and then keep refining it till you have more time. And we focus on the first part, which is how do we quickly find a feasible solution. So this brings us to our problem formulation. So a general search-based algorithm looks something like this. We have a start and a goal vertex. We have a function called successor, which, given a vertex, returns all the adjoining vertices and edges. And we have an evaluation function, which takes an edge and the world representation to ascertain the validity of that edge. And we have a select function, which selects which node to expand next. So we maintain these three lists, which is like the open list, which is a set of all nodes that are candidates for expansion. The closed list, which is like all the nodes that have been expanded, and the invalid is the list of all the edges that have been found to be in collision. And then while the goal has not been added to the open list, we select something from the open list using a heuristic function. And then we expand it to get all the valid successors and all the invalid edges by checking against the true world. And then we update all of our lists. And we do this till the goal is in the open list, and then we return a path. So our key insight is that we can actually think of this search process itself as a sequential decision-making under uncertainty. Oh, and the uncertainty is over the world map. So the state of the search is the concatenation of these three lists, the open list, closed list, and the invalid edge list. And at every time step, we perform an action, which is to select something from the open list. And then and then the environment essentially expands that and checks all the edges for validity, and then we update all of our lists. And the transition function is something that depends on the hidden underlying world that we don't know about. And in this view, we can think of heuristics as policies. So a heuristic is essentially a classifier that takes the current uncovered world and the state of the search tree and selects which node to expand based on minimizing the number of expansions. And since the reward is -1 for every expansion, in this view, we can think of the optimal policy as one being that minimizes planning effort explicitly. And there's been a lot of related work in this field. So a lot of work on learning heuristics for planning. But this work, they usually do not consider the non-IID nature of the sequential decision-making process. There's also been work on deep learning for planning. So how do you incorporate long-term planning in your RL or deep learning agents? We're also interested in something similar, but we focus on graph search. And we also leverage a lot of work on imitation learning of oracles, and which usually boils down to this non-IID supervised learning under your own state distribution. So now we shift our focus to how we can learn such heuristic policies. The first question that arises is, how do we represent the search state? So right now we said that the state is a concatenation of these three lists. But we can actually compress that to get a feature vector for every node in the open list. And we get like these two kinds of feature vectors. One is search-based, which is like where is it in the search tree, and where is its configuration in the world, and some naive heuristics like Euclidean distance and Manhattan distance. And we also have some features that are based on the environment uncovered so far. So we can have distances to obstacles in the invalid list and stuff like that. And another important thing to note is that the feature calculation itself should not expend extra search effort by probing the environment extensively. So given this MDP formulation, we can think of learning a policy using model-free RL. But since we have a very large state space, which is growing exponentially as more nodes are added to the open list, and we have a sparse reward, which is that we only get like 0 when we add the goal to the open. Exploration in these models, in this domain, is very difficult, and these these algorithms are slow to converge. But we can actually do better. So our problem has a very good structure to it that we should not ignore. At train time, essentially, we can solve the entire problem and construct an optimal oracle that knows the true number of expansions to go for every node in the graph. And we can do this using backward Dijkstra's algorithm. So while the learner tries to approximate the search effort from its current uncovered environment, this oracle has solved the full problem and knows the true expansions to go. And such an oracle is called clairvoyant. And there's been some work by Sanjiban on how we can still bound up performance when we are dealing with oracles who essentially have more information than us. So we use the paradigm of imitation learning with cost to go. So essentially, we're trying to learn this function approximator by regressing to the oracle's Q-value estimates. And given a world sample from a prior distribution of worlds, uniformly sample time step t, and the distribution that is induced by the roll-in policy, we are trying to minimize this expected squared error with respect to the oracle. And we're trying to find a parameter vector theta that minimizes this error. And then after that, the planner can follow a greedy policy with respect to explicit search effort. That is, the node that it expects will have the minimum number of expansions in the future. The problem is that if we just use the oracle, we'll face this well-known distribution mismatch problem in behavior cloning, where as soon as the learner makes a mistake at test time, it'll enter a state space, enter a region of the state space where it does not know what to do, and it'll get lost, and its errors will compound over time. And the solution to it is using iterative learning, where we roll in with a mixture of the oracle learner, and we aggregate the data set. And this is well formulated by Ross and Bagnell in their aggravate formulation in 2014. So this brings us to our algorithm, search as imitation learning, or SAIL. We run n iterations of the algorithm, and in each iteration we run m episodes. And in every episode, we sample a world from a distribution. We roll in with a mixture policy up to some uniformly sample time step t, and we select an action. We then query the oracle for the true search effort given this action or given this node. And we aggregate this data with all of our previously collected data. And we do this k uniformly sampled time steps in one episode. So we get k data points at every episode. And then we train the next policy on this aggregated data set, and we do the above to get like n different policies. And we return the best policy that we have found on validation. Now I'll discuss some of our evaluation of the SAIL algorithm. So first, I discussed some benchmark experiments. And these are 2D experiments where the world is a bitmap of obstacles. Start and goal are kept fixed to bottom left and top right, and our graph is an 8-connected lattice. We represent our Q network as a standard feed-forward neural networks with 2 layers of 150 units and ReLU activation. And we compare it with a bunch of motion planning and machine learning baselines. Some of them are like adaptive motion planning baselines like MHA star, and for machine learning we study behavior cloning and some model-free RL algorithms. So this shows that we can actually we can robustly learn a competitive policy across all our data sets and outperform all the baselines. This is normalized evaluation cost on different or normalized number of expansions on different data sets. This is a good key observation that this algorithm can actually learn to exploit the configuration of the environment. So in an environment with gaps, it can learn where to search for gaps and slide along obstacles. And in an environment with mazes, it can actually learn these axis-aligned motions, which are an effective strategy. Also, it can escape local minima. So a quintessential example in motion planning where greedy algorithms are known to always get stuck is this bug trap. And SAIL actually learns how to backtrack away from when it finds an obstacle and search in different directions to find a way out of the bug trap. And it also consistently converges fast across environments. So by the 5th iteration, it can already find a competitive policy. And it also converges faster than model-free RL, which either does not converge or it takes too many iterations to do so. So now coming back to our original motivation of the helicopter. So we construct this parametric distribution of canyon-like environments. And the robot has to navigate in the middle of the canyon. And in this example, we can see that while optimal A star fills the entire canyon with expansions because it does not have any context of where it is, SAIL, on the other hand, can learn to focus only on the middle of the canyon and backtrack away from obstacles. And it gets like 100 times lesser number of expansions. And we also test this algorithm on a real robot. So this is our DJI M100 flying at high speeds. And so what happens is it encounters these no-fly zones, which can be, say, other vehicles, or it can be buildings and stuff like that. And these form a complex environment, and it has to respond in real time. So in this example, we train it only in simulation on these sort of mazes. And then the planning is done on the robot on board, where it encounters these no-fly zones, which form a maze-like environment. And it can find this policy of hugging the maze and reaching success, whereas optimal A star is not able to solve the entire problem. So in summary, this brings us to a few key takeaways. The first being that motion planning should focus on expected performance, and graph search is generally a good representation. And graph search can be thought of as this MDP over space of lists, and a good heuristic policy can be learned for it by imitation of optimal planners. And also future work that we're looking at is how using recurrent architectures to represent the heuristic function, and at any time planning to incorporate solution cost, and generating realistic data for training using some photorealistic simulations like Microsoft Airsim. Thank you.
Do we have any questions? No. I may have one. So how specialized is your planner to the kind of environment that you train on? It seems it can work well with mazes, but if I now use that for a different environment?
OK, so I guess your question is how well does it generalize to the change in distribution?
Yeah, sure.
So I mean, it essentially depends on how heterogeneous your training data is. And sometimes in motion planning, you know that you're going to encounter some specific sort of artifacts, and you sort of want to like train for that.
Sure.
But in general, if you it will scale to like any different distribution that you throw at it.
Okay. Any other questions?
So can I just ask a bit about the when you showed the drone in the last couple of slides there? So you have a completely separate system that detects these obstacles and then generates like the map of obstacles, which the planning then uses, or how?
Yeah. So these obstacles, they're essentially no-fly zones.
Mm-hmm.
So sometimes, yes, they can occur dynamically, and you have a system that detects it. And the other times, they might also be in your problem formulation. So like you say, you already know that there are buildings over here that you do not want to fly over.
I see. Right.
Okay. So let's thank the speaker one more time.